is counterclockwise, the torque will be positive. That means that if I try to rotate something that way, it is going to be a positive torque. This will come in handy when we're doing our summation of torque. Sounds similar to our summation of forces, but we will be doing summation of torque. So if it wants to rotate this way, it's a negative torque. This is similar to when we would have forces and we had a free body diagram. If you had a force this way and this force was normally positive and that force was normally negative. Same thing, if you look at torque in terms of an increasing angle, you want to remember that this way is always positive. Think of increasing this as a theta. This is always positive theta. So you can think of that, oh, okay, that's a positive torque. And if you're going this way, right, you're actually increasing downward in the fourth quadrant, and that would be like a negative theta. So you can think of that as negative torque. Multiple torques. When there are two or more torques acting on an object, the torques are added. This should be similar to what we used to do with forces. We do our net forces are equal to ma, and if it's an equilibrium, our net forces are equal to 0. We are going to do the same exact thing with torque. If the net torque is 0, the object's rate of rotation doesn't change. It's going to be in static equilibrium in this chapter. That means that for most of the problems, it's going to say things like, if this object is on the verge of tipping, on the verge of rotating, meaning that it's at that threshold value where it's not in rotational motion, but it's about to be. So we can always assume that it's not moving. When the forces are parallel to the position vector, no rotation occurs. Think about this drawing that you see of a door, and I know that right now we're seeing it from a bird's eye view, like if we're above. If you were to be right in front of the door and I was to push this way on the knob,